Let me begin with a word of prayer. Heavenly Father, we thank you for this afternoon. Thank you for this time we have to study math together. Pray that you'd just guide our steps, help the students to understand the material, and just ask good questions as they think of them. Just pray that the students would be encouraged each day, Lord, to do their best for your glory. In your name I pray, Lord Jesus. Amen. Okay, so don't forget the top hat, obviously. So I hope you noticed there's an assignment which is due, when is it? Wednesday, right? Is that right? I think I said Wednesday. If I said Friday, tell me. I'm pretty sure I said Wednesday. So anyway, so the assignment is not complicated. All you need to do is to watch the videos that I posted last Wednesday, right? In those videos, I go over 10 long division examples, all right? And each one of those, I explain how that solves a particular problem, or at least I explain the interpretation of the long division, what it means, right? So the assignment, I'm not expecting you to work out all 10 of those long divisions, although of course that would be healthy for you, right? It's not bad to get extra practice, right? And those are practice problems for you. You can work through them in parallel if you want. I'm not asking you to do that and turn it in. All I'm asking of you is to fill in the answer from each example on the assignment sheet. So literally all you have to do is go watch the video, find the answer, write it on that sheet, and turn it back to me. It's worth 10 points. All right? You don't have to show your work. You just have to show the answers, which is to say, watch the video, find the answer, write it down, right? That's the theoretical minimum for this assignment. What would be wiser for you, of course, is to actually work out the examples for yourself. You get more out of it that way, right? But you guys might have time pressure, whatever. At least I want you to look through the videos and find the answers. So you should that will help you affirm in your mind what long division does for us, all right? Now we'll do more long division, probably not today, actually, because today I need to talk about reverse problems, unless there's a question about something. It's always time for questions, if you guys got questions. Yeah. We have 3 tests in this class. So there's test 1, test 2, test 3. And I think they're each worth, oh man, 150? Okay, good. Good, I forgot. So 150 points each. How much is the final worth? 300 points, maybe? 250? I forget. It is what it is. It says in the syllabus, right? But in practice, the final might be worth more for you, right? Because maybe you'll be replacing your test 1 grade with the final exam grade. So if that's the case, the final isn't really worth 250 for you, is it? It's really worth 400, because you're going to replace that test 1 grade with the better final exam grade, right? Some of you should be like, yes, I do not want my test 1 grade to stick, right? Right? Do you like college algebra? Do you want this to be a feature of your college experience? Like every semester you come and take this course? No! You want to be past this course after this semester, right? I don't want to see any of you next semester in this course, for example, right? So, meaningful steps towards that goal, start working out test 1 for yourself. If you got problems wrong, go attack those wrong problems, see why you got them wrong, try to fix it, right? If you're just stuck on something, come talk to me about it. I can try to help, all right? Okay, so I want to talk about reverse problems in here. So reverse problems, roughly speaking, here's the pattern of them. Is given some data, construct polynomial f of x to fit the data. All right. This is backwards of what we've been doing up to this point, right? Because up to this point, I've been saying, here's a formula for f of x, go graph it, right? Now I'm turning the tables. I'm saying, here's some data, find a polynomial which fits that data, all right? So example 1, given graph y equals f of x below, All right. Find polynomial of least degree which fits, gives the graph, such a graph. All right. So let me come up with a graph for us, all right? Here we go. Let's do something like this. Up and then down and then bounce and then up and then up like that. All right, there we go. And we're going to suppose that the y-intercept is at, I don't know, minus 20. All right. We're going to make this point right here be given, that's going to be given to be, say, minus 5. This will be at minus 1. It's bouncing over here at 1. And then there's a crossing over here at, I guess that's positive 5, isn't it? All right. So how do we find a polynomial that has a graph that looks like that? How do you do such a thing? Right? We haven't done any problem like this yet, right? This is backwards of what we've been doing. So I'm going to just work the first one, then I'll let you guys kind of participate more in the next example, okay? So here's how it goes. You just write down f of x is equal to a. So we want to leave that a there to adjust for the kind of scaling of the problem. And then I look at this x minus 5. I put an x plus 5 from that. Then I cross at x minus 1, so I put an x plus 1 from that. All right. I'm ignoring the minus 20 for now. I go over here to 1. I bounce at 1. So if you've got a bounce, you need an x minus 1 squared to bounce. Right? And then I want an x-intercept of 5, so I do x minus 5 there. That should do it. All right? This has the right shape. Now I have not yet applied the y-intercept, right? What is minus 20 equal to? It's equal to what? It's equal to f of what? Of 0, right? That's when x equals to 0 at the y-axis. So we unplug in 0. But what is f of 0 for my formula? So minus 20, right, equals f of 0. But when you plug 0 in, what do you get? You get a, right, times what? Times 5, times 1, times minus 1 squared, times minus 5. In other words, we have an equation, one unknown involving a. We can solve for a, right? I think that's a minus 25 on the right-hand side. I think I've got minus 20 equals to minus 25a. So what's the solution? If I divide by minus 25, I get what? 20 over 25, right? A equals to minus 20 over minus 25, which is also known as 4 over 5. So lo and behold, the answer, f of x equals to 4/5 times x plus 5 times x plus 1 times x minus 1 squared times x minus 5. And there you go. That is a polynomial which fits the graph. Everybody top-hatted? 25. Yeah.
Why is it x minus 1 squared?
What's the difference between 1 and all the other x-intercepts?
It bounced.
It bounced there.
Oh.
So that's why we want x minus 1 squared there. And I mean, technically, I could make it to the fourth power. It would still make it bounce, right? But why do I not do that? Why do I not make it to the fourth power? Why don't I put x? Least degree, right? So this is the smallest order things I can get away with and get this graph. Yep. I did not close the top hat. It is open still. So I'm not sure what to say about that. I mean, it shows open on mine. It's not working? Anybody else? 3, 4, 5, 6, 7, 8, 9. All right, just a second here. Let me try something else. Just for you. This is your secret code. Can I have your pen? Oh, wait a minute. Is that a white pen?
No.
Can I?
It's not open.
Oh, it's a, yeah. Well, that's hard to write with, isn't it? I'm creating an attendance just for her, too. That way.
What's the top
Did you already? But did you already do it?
Yeah, we get extra credit.
No. This is just for her. No. Because then it will undo the whole point of this. All right, there you go. Sorry to waste time with this nonsense. I honestly, anyway, I digress. Example 2. Same instructions. As example 1. All right. But this time, the graph will look a little bit different. All right. And so here we go. Suppose we have a graph that looks like this. We bounce, cross like that. All right, there we go. And let's see, let's put this at -8. We'll put the bounce here at -5. This is at -0.3. And this one over here, we're going to say is at 4. All right. And I'm going to also tell us that this point right here is at 2, I don't know, 10. Obviously not the scale, but suppose 2, 10 is a point on the graph, all right? So I didn't give us a y-intercept this time. I gave us a different point, all right? I'll probably regret that -0.3, but let's get to it. So what are we going to, let's start building our function. So we want f of x equals to a. We want a constant to adjust so we can set the vertical scale, basically. And then what? How do I take care of the -8? What do I want for that? X plus 8. X plus 8 gets the -8. That's the smallest order that you can get and get a crossing. X plus 5 squared, because we want to bounce at that -5. So x plus 5 squared. Yeah, x plus 0.3 squared. All right, great. And then what? X minus 4. Very good. And then what do we know? That 2, 10 being on the graph, what does that tell us? Right, this means f of 2 is equal to 10. So I can plug that in, and I get 10 equals f of 2, which is a times, what's 2 plus 8? 2 plus 8 is 10. 2 plus 5 is 7. 7 squared is 49. And then times 2.3. Oh, man, I wish I had my calculator. Oh, and that's squared, too. 2.3 squared, and then goodness gracious, 2 minus 4 is minus 2, yeah? So apparently, A is equal to 10. Oh, we can cancel the 10s, right? Woohoo! See that? Look at that. Gone. So A is the reciprocal. It is 1 over 49 times 2.3 squared times minus 2.
Where did you get the 1 from again?
The 1?
In the fraction.
Oh, well, this, when I cancel the 10 out, I get a 1 over here, right?
Oh, okay.
Yeah. And then I don't think I have the, yeah, my son has my calculator at the moment. You guys will have to tell me what, I mean, we can leave it like that number if you want. Second here, let me phone a friend. Do, 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 do. So, fun fact, that's, wait a minute, is that a, my friend is not being helpful. I guess that might be 50 over 25,921, but anyway, let's, I regret that 0.3.
It's
Made,
negative 518.42.
that's the bottom, isn't it?
Yeah.
I get 0.001929 minus 0.1. Oh man, I can't remember anything. 0019. 19289. Sorry about this. I try not to bring ugly decimals into these examples. This is my poor planning on my part. Anyway, so that's roughly it. So the function then is f of x equals to minus 0.0019. I mean, to be fussy, I really should put the exact number that's above it. But f of x approximately equal to this times x plus 8, x plus 5, x plus 0. So you can expect that 0.3 would not be on a quiz or a test. That's just poor. That's just a really dumb move on my part here 5 minutes ago, because it just made it ugly. So sorry about that. Anyway, setting aside the ugliness of the leading number, does it make sense that it's negative? We should have expected that, right? Because the graph overall, it's like even degree and it opens down, right? So that's got to be, the leading coefficient's got to be negative for this general shape. Example 3. Okay. So find polynomial of least degree with x-intercepts of, let's say, minus 4 comma 0, minus 1 comma 0, 3 comma 0, such that let's say 2 comma 7 is also on graph. So this time, no picture, all right? I'm just giving you information about it, all right? So how do we do this one? It's not so different, right? This is a super secret extra top hat code. Share this with no one.
Appreciate it.
Uh-huh.
Okay. I realized why that wasn't working earlier.
Yeah, it's. We had problems earlier, so I had to make up a new,
Thanks.
and even more stupid code for today. But. Uh-oh. He saw it. This is why I can't play poker. Anyway, okay, so let's see. Let me start us out. F of x equal to? We're going to put an a out there because we want to be able to adjust the size of the graph to fit the point that we're given. The x-intercepts, we want what? X plus 4, x plus 1, and x minus 3. So I'm just working the factor theorem in reverse. If I want those to be x-intercepts, I need those factors, right? And I want least degree, right? There's no bouncing here. I mean, you could make it bounce, but then you'd have a polynomial of larger degree, which is not what we want, right? So this formula has these x-intercepts, right? And now what's left? 2, 7, right? So if 2, 7's on the graph, what's that mean? It means f of 2 equals to 7, right? So let's try that out then. 7 is f of 2, but here that's a times 6. And what's 2 plus 1 is 3. 2 minus 3 is minus 1, right? So when I plug in 2 into the formula, I get minus 18a actually when you work it out. So then we solve for a, and we get a equals to minus 7 over 18. And so the answer in this problem is f of x equals to minus 7 over 18 times x plus 4 times x plus 1 times x minus 3. All right? So I have an important question to ask you. Did I multiply any of these answers out? So on the test or the quiz, which is coming up, should you multiply these answers out? The answer is no, right? Part of what I do in here is I try to model how I want you to solve problems, and I don't want you to have to multiply these things out unless I specifically intend it. How could I specifically intend it? I would include extra wording. My extra wording would be, find a formula for f of x in standard form, right? Standard form is when we have it multiplied out. But unless you see that language in standard form, you don't have to multiply it out. All right? Don't do that. It's a colossal waste of your time. Many of your predecessors have wasted many minutes doing this, so don't do that. And let this not be a self-fulfilling prophecy that I'm making right now. Yes? Okay. Anyway, example 4. This one's going to be a little bit different. Actually, it's going to be a lot different. This is a question about a parabola. Parabolas are special. We know lots of things about parabolas, right? So given y equals f of x is parabola with vertex, let's say minus 2 comma 7, and its graph passes through, let's say 1 comma, 10, all right? Find the formula for f of x in, now I'm going to do it standard form. All right? So let's see if we can do this. This one's, again, different than the previous ones because here we have very special information. It's the vertex of the parabola, right? So we remember we learned the vertex form for the parabola. We should go back to that, right? What's the vertex form for the parabola look like? What was the formula? It was a times x minus h squared plus k, right? Gives vertex at h comma k, right? This is the formula whose graph is a parabola with vertex h comma k. But we're given h is what? H is minus 2, right? K is what? 7, right? So look at this right here. This tells us, that tells me that h equals minus 2 and k equals to 7. So I can put that in here and I get y equals to, f of x in fact is a times what? X plus 2 quantity squared plus 7. All right. Now what's my next move? What have I not used yet? There's another piece of information I have not applied yet to our solution, right? It passes through 1 comma 10. What's that mean? So we could write it this way in terms of math language. 1 comma 10 is an element of the graph of f, means that f of 1 is equal to 10. All right? Plug in 1, you get back out 10. But we also have a formula, right? So this gives us that 10 is equal to a times 1 plus 2, right? Squared plus 7. What does that give me? That gives me 9a equals to 3. So 3 is equal to 9a. 1 plus 2 is 3. 3 squared is 9. 10 minus 7 is 3, right? I'm subtracting 7 to the other side. Now divide by 9, what do you got? We got a is equal to 1/3, right? So what's my formula? So my formula is, I'll do it over here, f of x equals to apparently 1/3 times what? X plus 2 quantity squared plus 7. Now, if the instructions to the problem were just find a formula for the parabola whose graph has this data, then that could be the answer, right? But this time I said find the formula in standard form, right? So we've got more work to do. We need to multiply it out. Yeah? So this is what? This is 1/3. X plus 2 squared is x squared plus 4x plus 4. Then I've got plus 7. So multiplying that through, I've got 1/3 x squared plus 4/3 x plus 4/3 plus 7. So what is 4/3 plus 7? How many thirds is 7? It's 21/3, right? So 21 plus 4 is 25/3. So the answer, and of course you could use your calculator. I would, but my children stole it. 25 over 3. So there you go. That's the answer there. So any questions about this material at the moment? Listen, there's a bunch of homework problems on these, right? So I'd like you to go try them, chew on them, see if you can do them. Maybe you've already done some of them. If so, great. But you try them. If you get stuck on them, come back here or ask me about them, all right? But we're going to move on. We're going to move on to graphing rational functions, all right? Now, I really owe you I'd like to give you, remember I had that algorithm for graphing polynomials, like the steps we can go through to graph a polynomial. So I want to give you a list of steps like that for a rational function, but there's a lot more to it, and we don't really have quite enough time today to do the algorithm justice, so I'm just going to dive straight into the examples for rational functions, and we're going to proceed like that. Hope that's okay. Now next class, if all goes as I hope, I'll probably start with the algorithm, and then we'll do examples to exhibit how that algorithm plays out. So there is a recipe here. And the recipe for graphing rational functions is very, very much like what we already have for graphing polynomials. Like basically the starting move is to graph to factor everything in sight. That's like a lot of it. But so let me get started here. I guess the first order of business though is what is a rational function, right? I just used the term rational function like you guys know what I'm talking about, but that's probably ill-advised, right? So let's talk about graphing rational functions. So first order of business, I need to tell you this much. If we have f of x equal to p of x over q of x, where both p of x and q of x are polynomials, all right, then f of x is a rational function. So rational functions are like fractions if polynomials are like numbers, like integers, right? They're like the fraction function, so to speak. So rational functions are more challenging to graph than polynomials because they have vertical asymptotes sometimes, and they have holes in the graph sometimes, and they still have x-intercepts sometimes. All right, so let's look at an example. Let's try to graph y equals to f of x equal to, let's say, x plus 3 over x minus 2 squared. All right. So I took it pretty easy on us in the sense that it's already factored for this first example, all right? So what you do is you look at your formula, you identify any place where the denominator or the numerator is 0. This is what we did before when we were solving rational inequalities, actually, I believe. So it's that song and dance again here. So make my number line. Right, so my number line's got a minus 3 on it, and it's got a 2, all right? Let's see here. So here-ish, all right, 2. I'm going to graph under that. Just go ahead and put my graph's going to be down here. So I kind of like use the number line as I try to mirror it like that. And here's the deal. Wherever you have division by 0 unopposed, which happens here at 2, right? That gives you a vertical asymptote. So in this case, there's a vertical asymptote at 2. All right? There's a vertical asymptote at 2. So I usually draw a dotted line for the vertical asymptote. All right? Okay. I'm getting ahead of the story a bit. We need to do what to this number line here? We should add pluses and minuses, right? So plug in a point, see what happens, you know? What happens if you plug in, like, I don't know, 3? That would put us over to the right, right? If I plug in 3, I get 6 over 1. I get a positive, right? So I start out positive. Then, check this out. Because this is a squared factor, we bounce. All right? So we stay positive up in here because this is x minus 2 squared. Now this x plus 3 is power 1, so we flip from plus to minus again. So the sign flip theorem still works for rational functions, like we just have to keep track of you have an even or an odd order to your factors, all right? But what we mean by bounce is a little bit different now, okay? See, if we're talking about an x-intercept, we could have a bounce there, right? Like we're just talking about for polynomial graphs. But let's get through it here. So the other thing I need to say is that here, I should also make this comment. The the degree of x plus 3 is equal to 1. That is less than the degree of x minus 2 squared, which is 2, right? What that means is that eventually, y equals f of x goes to x-axis, which is what I'm trying to say is that it has a horizontal asymptote of the x-axis. The graph is getting dragged into the x-axis eventually. It's got to drift to the x-axis eventually. All right. How about this minus 3? What does that tell me about the graph? It's a what? That's a place where the numerator is 0, right? See that? Minus 3 makes this expression 0 over some number. The point is, it's 0 when we plug in minus 3. It's defined. It's just 0. That's a x-intercept. So that puts that point on the graph. All right? Then what's going to happen here is it crosses from negative, right? And crosses from negative, and then it does something like this. It goes up like that, and then up here it's still up, and then it goes back down like that. And so what has to happen over here is it has to kind of like eventually curve back up to like that. So roughly speaking, this is the graph, something kind of sort of like this. I'm doing my best here, but there's sometimes it's hard to get the shape. My shape is qualitatively right, but I think if you actually ran it through a graphing calculator, it would probably look a little different. But this is essentially what the graph looks like. The most important features here is that you have like a volcano at the 2, and you've got a x-intercept at the 3, a minus 3, right? And it asymptotically, it goes to the x-axis like this. So, see, you could think of this as like a bounce, right? My brother teaches this. He likes to say it bounces off infinity. In this case, it's like bouncing off infinity. Let's look at another example. Suppose you have y equals to f of x equals to, let's say, x squared minus 9 divided by x squared minus 4. All right? And yeah. And then we'll multiply this thing by x plus 3, just to make it interesting. All right, that'll be our example 2. How would we graph this thing? So here, I got work to do, right? I've got to factor this before I get too far into it, right? So what happens here is you've got x plus 3, x minus 3, divided by x plus 2, x minus 2, times x plus 3. Yeah? And, oh look, there's a common factor above and below. Do you see it? See that? So this here, when you have this phenomena, when you have this and this the same, what that means is that there is these two things together mean hole in the graph at, x equals to minus 3, all right? So for x not equal to minus 3, what this function looks like is just what? So when x is not equal to minus 3, you just have that this is equal to x minus 3, over x plus 2 times x minus 2, right? This is for x not equal to minus 3. This formula applies. All right? So what I just did, this is called the reduced function. All right, so this right here is the so quote-unquote reduced function. So the reduced function basically is what you get if you fill in the holes in the graph, you get the reduced function. So when you have a problem like this, the way to graph it is just to graph the reduced function basically and then put a hole where it's supposed to be. Yeah? So anyway, let's do it. We've got our number line, all right? Where are my critical numbers? We've got 1 at minus 2. We've got 1 at 2. And we've got 1 at 3, right? And there's also, I mean, you got to be careful. We should really include the, to be fussy, really you have to include the hole in the graph as well. And the reason for that is you could have the hole in the graph happen at a x-intercept. And so that'll get you into trouble if you're not watching out for it. So let's just include let's include the hole in our number line just to be safe. Now, so I'm going to go up here, and what happens if you like plug in, 4? You get plus, 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 right? So we start with positive here, and then you get to 3, x3, right? That's from this x minus 3. How many x minus 3 factors are there? Just 1, right? So we flip signs. And then we get to 2. How many x minus 2 factors are there? Just that one. So we flip signs. Then we get to minus 2, which is the x plus 2 factor. How many are there? There's just that one. So we flip signs. And then something interesting happens. At minus 3, that corresponds to x plus 3. How many x plus 3 factors are there? 1, 2. There's 2 of them, so we don't flip signs. So we stay negative. Right? If in doubt, try plugging in minus 4 into this. See what happens, right? If you plug minus 4 into this, you'll get positive, positive, and this becomes minus 1. So you get a net of plus, plus, minus, which is minus. Just do what you want to check it. All right, great. Now we graph. So we got the y-axis right in the middle there. And like these. And how about this one? Again, the degree of the numerator is 2. The degree of the denominator is 3, which means that, again, we've got a horizontal asymptote of 0. Eventually, it's going to get dragged into the x-axis. OK, where are my vertical asymptotes for this one? The vertical asymptotes are coming from where you've got 0 in the denominator, right? So vertical asymptotes are the minus 2 and 2. Right? Now these ones, unlike the last one, we're not going to bounce at these vertical asymptotes. We're going to cross the x-axis in some sense. Not that we actually, I say in some sense, you'll see why, right? Let's see here. And then at 3, we have a x-intercept. So that's right here. Yep. Let's see here. What else? What is f of 0? Just to make my graph a little bit better. What's f of 0?
Did you just plug in 0 for the vertical asymptote?
Yeah, plug in 0 into the formula, right? We get minus 9 over minus 4 times what? Times 3, right? So that gives us a 3 over, looks like a 3 over 4, right? So it's positive like we expect, and it's about 0.75. So if I'm going to use the same scale on the y as I'm doing on the x, and you don't have to, of course, right? But if I am, this is at minus 2, this is at 2, right? This is 3 over here. So 0.75-ish is, kind of sort of here. So here's another point on the graph, yeah? All right, so what's going on here? We're approaching infinity from the right here like this. All right, then I need more, I need more graph. There we go. Then we cross 3 here, right? And then what has to happen is you have to get drawn back up into the x-axis. Eventually it goes to the x-axis for large values of x, right? Now what happens here? Oh man, did I do that right? No, come on guys, let me get away with that. Is this right? It's positive, right? I mean, excuse me, it's negative between 2 and 3. So what's it supposed to look like? The exact opposite of that, right? So basically up through 3, and then eventually comes back down, like so. All right. So let me get rid of the offending. Oopsie, oopsie, oopsie. There we go. All better. So I've got, it's negative here. It goes through the x-intercept at 3, and then it comes back down to 0 because the y-intercept is, the y-asymptote. There's a horizontal asymptote of 0 eventually. Now it's positive here, right? So it's like this, right? And then it probably just looks like this. That may actually be the turning point. I really don't know for sure, but it looks something like that, right? There's no x-intercept between here and there, right? If there was, there would have to be a factor in the numerator to make it so, okay? Didn't happen. There's no x-intercept, right? If you want this graph to look exactly the same but bounce off the x-axis, you could just take this formula and, oh, I shut up. If I do that, it causes other problems. Never mind. Sometimes I get carried away with what I can do on the, like modifying a formula. There are unintended consequences for what I was thinking. Let me go on here. So we got that much. Then we get here. So you notice what happens is we're negative on the other side of the asymptote, which means that we got one of these guys, right? And then it stays negative, so it just keeps going like that, all right? Now, it's not done yet. What else is there? The hole. Where is the hole? The hole is at negative 3. So where is it then? I mean, yes, it's kind of here, right? So the hole in the graph is right there, right? Its coordinates are -3, comma what? And this is where you can use the reduced function to figure out the y-coordinate of the hole in the graph. So the hole in the graph at -3, we plug in, use this, find the hole. So we do -3 over -3 plus 2 times -3 minus 2, whatever that is. So I'm plugging -3 into the reduced formula, all right? And what happens? You get what? A -6 over, looks like -1 times what? -5 times -5, right? So we got -6/5. So this point right here, if I did it right, would be at -6 over 5. You have to use the reduced function to find where the hole in the graph is because the original function is not defined at -3, right? If you plug -3 into this, you get division by 0. You can't do that, yeah? So you guys ever seen a hole in the graph before? Yes, no? Do you know how to put a hole in the graph wherever you want? Like here's your final example for today. Here's a graph. It goes through 1 and 8, and so y equals to x minus 1 times x minus 8, right? We all good on that? That's just factor theorem, right? Where do you want to put the hole? Put it wherever you want. You guys choose. Where do you want to put it? Put it at 0? You want to put a hole right here. The way to do that, very simple. You just take this formula and multiply by x over x. That punches a hole at 0. You want to put a hole at 9? Just multiply by x minus 9 over x minus 9. That punches a hole in the graph. It's a mathematical hole puncher. It's a very silly formula. They make sense everywhere. They're equal to 1 except for where they're not defined, which is to say they punch a hole in the graph. Anyway, thanks guys. I shut up. Good day to you.